In this section, we're going to be looking at how to compute limits analytically, and what this means is we're no longer going to have to build a table and plug in values very close to compute a limit, and we're also not going to have to take the time to draw the graph. We're going to be able to work just with equations and a little bit of algebra in order to solve some limits. For many functions that you encounter that you've seen so far, and for most points, so for what we'll call for now well-behaved functions, we may evaluate limits by substituting c into the function f of x for x. And this is called direct substitution. This means that the limit, we're going to be able to find it by just putting in x for c. So as an example, the limit as x approaches 2 of the function x squared plus 3, we can actually find by just taking 2, squaring it, adding 3, and determining that this number is 7. Functions that you can do this for are going to be called continuous, and we're going to talk about this a lot more in a few days. But for now, we just want to start to recognize what are some limits we can follow by this idea of direct substitution, that is subbing in. Now, one thing that's very important now that you're in college is to recognize that we're going to substitute and compute. We no longer plug and chug. Okay? Very important. I take this very seriously. We're going to substitute and compute. So first we have some basic limit rules that are going to help us out. The first one says that the limit as x approaches c of b, where b is just a real number, is going to be equal to b. Constants are constants. Property 2, the limit as x approaches c of x is equal to c. We can directly sub in. And the limit as x approaches c of x to any power n is going to be c to the n. So these are good rules to memorize, but we also want to understand them a bit by looking at their graphs. So here we have graphs and limits that show off these three basic rules. The nice part is we don't need to look at the graph anymore as long as we really understand what the rule is telling us. So in the first case here, we have a limit, and if we look at the graph, our function is always 3. Now our function is 3 all the time. It's always 3. No matter where you are, it's going to be 3. So this means if we try to compute the limit, well, what happens as we get closer to 2 on both sides? If we follow along the function, we're getting really close to 3 on the right. We're also getting really close to 3 on the left. So this means overall, our answer is just 3. Our function's 3 all the time, so the limit's 3. Nothing too crazy going on here. In our second example, we want to compute the limit as x approaches 2 of the function x. I've drawn the graph of x here, and again, we think, well, as we go towards 2 from the left and the right, we want to think what happens. So we follow along our function. From the left, we're getting darn close to 2. From the right, we're getting close to 2. And there really wasn't anything special about this number at all. That is, our limit we can solve by directly substituting in 2 for 2. Last, in our third limit, again, we want to get close to 2, but this time our function is x cubed. And so we think, what happens as we get close to 2 from both sides? Well, this side's going on up, this side's going on down. Our function doesn't have any holes or breaks or anything that makes the limit not exist. So what we can do is we can write that this is simply 2 cubed. We can directly substitute 2 in for x, and we're good to go. And for those of you who like to simplify, this is of course just the number 8. So these are some very basic rules. The problem is they're all pretty simple and they don't get you very far, so we want to think about ways that we can expand and use them to figure out other things. So now we have some properties of limits that are really going to take us places. The key to this property, this theorem, is that if you have b and c, two real numbers, n a positive integer, and f and g functions such that you've already computed the limits of them, you know what these are, then what we can do is we can figure out a lot of other limits pretty quickly. So the 5 rules rather, are the scalar multiple rule, which basically says if you have a constant inside a limit, you can pop that out of the limit. If you're adding or subtracting two things that you already know the limits of, you can just add and subtract their limits. If you're multiplying two functions and you know they have the limits exist, you can multiply their answers. Same with division, same with powers. So let's see this in action here. Let's suppose that we wanted to compute the limit as x approaches 2 of 3x squared plus 7. Well, what we can do is we can think to ourselves, well, if I want to compute this limit, I should try to break it up. And I can break it up across the addition into two easier limits here. So this is using property number 2 there, that I can break the limit up. Next I look and I see what else can I do here. Well, this 3 is just a constant, and property number 1 says that I can move constants out. So what I can also say is this is going to be equal to 3 times the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 7. And now that I've simplified this quite a bit, what I can do is I can do one more thing. So if we go back to the basic limit properties we talked about before, well, the first limit here, this is just a power rule, which means I can directly substitute in. I can replace all my x's with 2 to get 3 times 2 squared. And last, this second limit here, well, this is a constant. And the constant rule says this function is always going to be 7, so that when I go to compute the limit, I'm just going to get 7. So my answer is 3 times 2 squared plus 7. And for those who really like to simplify things, my answer is 19. And what I think here is I think this is a really, really great complete answer. The goal is not this final number here. That's only part of the answer. Every single step here along the way is part of the answer, with the exception of these little boxes here. I just drew those in for me. But you should really break apart your limits and steps, show all your work. And the reason for this is because partial credit is great. So if you haven't copied these properties down, you should take a minute to copy them down, because I'm going to make them disappear as we talk about a few more things. As I just mentioned, partial credit is awesome. You should always show your work. Suppose, I don't have to suppose, I know someone's going to do it. Some student in this class is going to think, well, I don't need to show my work, I'll be fine. I'll do this in my head, and let's see, I ended up with 34. Now this poor student got the wrong answer, didn't show any work, so they're going to get a 0. There's no credit I can possibly give this student for anything. Now let's think about what this student might have actually been thinking. I bet what this student did is they just worked a little too fast, and what they were thinking was, well, I can break this up, and what I can do is I can just quickly throw my numbers in there and go ahead and compute, and I got that answer. Now the problem is this student, they got the wrong answer, right? So they can't get full credit, but they can probably get a lot of credit. They attempted to substitute in, and what I think they did is they just went a little too fast, and their 2 became a 3. They can get some credit. They should work slower, they should work more carefully, but they've shown me something. They can get a little bit of credit. What the student also could have done, if they worked slowly, is they could have written even more steps in here. They could have said, well, I'm going to break this up into 2 separate limits here, and then I'm going to substitute in a little too quickly, and I'm going to get my answer. Well, this student loses a little bit for answer, but they showed a lot of work. This student's going to get a bunch of credit, because I think they know what they're doing. I think they can compute limits. They just sometimes move a little too fast. Not full credit, but a heck of a lot of credit. As a final example, let's suppose a student decided to try to compute this limit here, and they said, well, my answer is 19. Did it all in my head. Once again, no credit. I haven't seen that you know how to compute limits. Honestly, I'm not asking you this question because I'm really concerned with the answer. I'm concerned with whether or not you can compute a limit. If I wanted to, I could figure out the limits on my own, or I could look it up in the back of the book. What I want you to show me every time is that you know what you're doing. Oh, and here's a fun little problem. You should also try this along with the other problems you need to bring to class, and we'll talk about it. Those are on Blackboard. This one isn't. Consider a function f of x with the property that the limit as x approaches a of f of x equals 0. Now consider another function g of x defined near a. Well, then it must be true that the limit as x approaches a of f of x times g of x equals 0. So for example here, let's suppose we know that the limit as x approaches 0 of x definitely equals 0. This is just a good substitution problem. Is it true that the limit as x approaches 0 of x times g of x will always equal 0. Is this always true? Or can you find a g of x that makes this not work, that breaks it? So try this for a little bit, think about it for tomorrow. Bonus points if you figure it out. So we want to quickly talk about polynomials. So that function we had in the last limit problem, 3x squared plus 7, you might remember is a special type of function called a polynomial. Now in general, polynomials look like this. They look like pretty nice looking functions, but there are two special properties of polynomials. One is that the coefficients, the numbers out in front of the x's, can be any real numbers that you want. And also the exponents, the powers on all the x terms, have to be non-negative integers. And this one, of course, is just x to the first, and here we don't write it because it's x to the 0 at the end. Now, what's nice about polynomials is that you can go ahead and substitute and compute these right away. You don't actually have to go about breaking them up. The reason for this is because every time you break them up, you're going to do the same thing. If you wanted to compute the limit as x approaches 1 of x cubed plus 2x plus 3, well, what you'll do first is you'll break it up across the additions, so you'll have 3 separate limits. And then, of course, you'll either substitute directly into these or use the constant rule to substitute again. And so we're going to skip the middle step and go right from this first part down to subbing in. There's no reason to take the time. And so we can wrap this up in a nice little thing that we're going to call the theorem. So our polynomial and rational function theorem is really nice. It says if you've got yourself p, a nice polynomial function, and c is a real number, go ahead and just substitute and compute your limit. It also says that if you've got yourself r, a nice rational function, which we'll remember is what happens when you divide two polynomial functions, and as long as you don't make your denominator 0, go ahead and just substitute in. So let's look at an example here. Suppose you needed to take the limit as x approaches 2 of x to the 4th minus 3x squared minus pi. Well, that thing right there, that's a polynomial, right? We only have integers for our exponents. We've got nice rational numbers, or real numbers for our coefficients rather. So what we can do here is we can just go ahead and substitute and compute. We've got 2 to the 4th minus 3 times 2 squared minus pi, and whatever that number is, grab your calculator and figure it out. That's your limit. And this is all you need to show for your answer. You just really need to show that this subbing in step, that you replaced all your x's with 2's, and you got some number out there in the end. Suppose you were faced with the limit now as x approaches 2 of x cubed minus x to the 1/2. Well, we want to be careful. This is not a polynomial, so we can't do this yet. We're going to save this one for later. Let's do another example. Suppose we take the limit as x approaches 1 of x squared minus 4 over x minus 2. Well, in this case, this is a good rational function. We've got a polynomial p over a polynomial q, so we can just try to substitute and compute. We're going to get 1 squared minus 4 all over 1 minus 2, and when we simplify this all down, I think we end up with just 3. And therefore, here's our limit. It's a good rational function. We can go ahead and substitute. No muss, no fuss. So one little warning example here is sometimes you're going to have rational functions that look pretty nice. And you're going to try to substitute in. You're going to say, this is a rational function. Let's go for it. Let's see, 2 squared minus 4 over 2 minus 2. Let's see, that's 0 over 0, 0. Wrong. This is a bad step. 0 over 0 is called indeterminate, which is a really fancy word for we don't know. I just don't know what the answer is. This is not the right way to find this limit. Some of these we'll be able to figure out. Some of them won't exist. We're going to need to wait. We need to make sure we don't divide by 0. So we had this limit before that we wanted to compute, but this is not a polynomial. Therefore, we can't just substitute and compute yet. But what we can do is we can look at this and we can think to ourselves, well, if this is going to work out, we need to be able to compute these two separate limits here. So we need to think to ourselves, well, how are we going to compute these limits? Is it possible that this limit exists? This first one is just a polynomial. We can substitute that in. But what about this last one? We want to be able to substitute it in. And it turns out we can. We have theorem 2.4, which tells us limits involving radicals. So as long as n is a positive integer, which it is in this case, 2 is certainly a positive integer, the following limit is valid for all c if n is odd, and is valid for c greater than 0 if n is even. Well, in our case, this is going to work. We can just go ahead and substitute because our c is 2. So this means our limit will be 2 cubed minus the square root of 2. And we can do this because these limits work out fine. These functions are nice, they're called continuous, and they give answers. But let's look at an example where it won't work. The limit, as x approaches negative 4 of x to the 1/2. If we try to substitute in, we're going to get that we need to take the square root of negative 4, which is, what, 2i? That's a complex number. So this limit, we're going to say, this limit does not exist because we can't actually substitute this thing in. It doesn't make sense. We're not going to take square roots of negative numbers in this class. Oh look, it's limit man. But more seriously, we're going to look at theorem 2.5, which are about composite functions. So the theorem says that if you have two functions, f and g, and you know their limits, that is the limit as x approaches c of g of x equals L, and the limit now as x approaches L of f of x equals f of L, that is, you can figure these limits out, then you can figure out the limit of the composite function by just going through and working through the composite functions. This is really just going to be f of g of c usually. So let's see how this works. Suppose you've got yourself that you want to compute the limit as x approaches 8 of x to the 1/3 minus 5, the whole thing squared. Well, the first thing you want to do is you want to rewrite this as a composite of two functions, a composition. So we're going to have an outer function, which is squaring, and we're going to have our inner function, x to the 1/3 minus 5. So this means in our theorem, our functions are going to be that we have f of x equals x squared, and g of x is equal to x to the 1/3 minus 5. And these, according to what we've done so far, are great functions. These are functions that we can just directly substitute into. It's not going to be a big deal. So according to our theorem, what we want to do is we want to figure these out in steps. So the first thing says that what we can do is we can figure out the limit as x approaches 8 of our inside function, which is just x to the 1/3 minus 5. We substitute in, and we get the cube root of 8 minus 5 is equal to 2 minus 5, which is negative 3. Then we compute that the limit as x approaches negative 3 of now our outside function x squared is going to equal negative 3 squared, which ends up just being 9. So that overall, our limit, our original answer, is going to be 9. Now the key feature here is that originally we had a limit of 8. We use it in our function. We directly substitute it in. And then the answer we get from the inside becomes the new limit for the outside function. We're going to do another one of these just to make sure everyone's on the same page. So you should take a minute to try to compute this limit on your own. The limit as x approaches 3 of x cubed minus 19 all to the 1/3. So if we do this limit in pieces, what we see is that we have the limit as x approaches 3 with an outer function to the 1/3 power and an inner function in our composite of x cubed minus 19. So this means in terms of the theorem, our inner function is x cubed minus 19 and our outer function f of x is x cubed. And these are both good examples of our direct sub properties. This first one's a polynomial, the second one is a simple radical power, and therefore both of them can use direct substitution. So this means when we go to write our answer, we want to write this, that this is going to equal, well, the limit can get moved inside because we both recognize that our outside function is a simple radical. We can now compute the inside through direct substitution because we have a simple polynomial inside our function. And so now it's just a matter of working through some simple arithmetic. Let's see, 3 cubed is 27 minus 19 on the inside becomes the cube root of 8, which is just 2. And this right here is a beautiful, beautiful amount of work to show. I recommend going through and doing these steps for yourself the first couple of times you work through these, just to make sure you understand why you can do the steps that you can do, because it's going to happen that you're going to get to these that you can't actually compute it, and you're going to want to think about why you can't compute it. Hint, hint, I might give you a problem that says, why can't you compute this limit, and you're going to need to know why. So you need to make sure with composites that both the inside and the outside functions are functions you can compute the limit of. So our last property of limits that we want to learn about today is what happens for limits of transcendental functions. So these are going to be our trig functions, sine, cosine, tangent, cotangent, secant, cosecant, and also our exponential and logarithmic functions as well. For all of these functions, basically what's going to happen is as long as the number you're using in your limit is a number in the domain of the given function, you can go ahead and just directly substitute it. That is, if we want to compute the limit as x approaches pi of sine of x, well, we can go ahead and just directly substitute and get that this is going to equal sine of pi. Because sine's domain is all real numbers, we can go ahead and just substitute that number in, compute whatever that value is, and that's our answer. We do have to be a little bit careful though. If we want to take the limit as x approaches negative 5 of the natural log of x, this is not going to be equal to the natural log of 5 because the natural log of negative 5 does not exist. Remember that the domain of natural log is only going to be from 0 to infinity, so we can't put negative numbers in. One more example here. Suppose we wanted to compute the limit as x approaches 0 of e to the x times tangent of x. Well, using our product rule, what we can do is we can break this up into two separate limits. The limit as x approaches 0 of e to the x times the limit as x approaches 0 of tangent of x. And what we do is we can directly substitute. We're going to get e to the 0 times tangent of 0, which overall is just going to be 0 because tangent of 0 is 0. So as long as you can really substitute it in, as long as it makes sense in the function, it's in the domain, you're good to go and you can directly substitute. If you have any questions, please post at least one of them to the website on Blackboard. Also try the problems posted on Blackboard, and I will see you in class. Thanks.